So in the last class, we tried to really look at these mathematical techniques about tensors, indicial notations, and so on, so stuff. What is the difference between Gibbs notation and indicial notation? How to simplify the things. Those are the things what we have discussed. Once we are having a reasonable grip on that mathematical notations, then it becomes easy for us to really write down certain quantities. The whole point of this fluid mechanics course is to estimate what kind of forces that particular fluid patch is experiencing. And then we realize that straight away talking about forces means center of masses. And there are issues or instances where center of mass might be outside the system and material may not be there. For example, here we are showing something like a sea wave breaking. There is something like a cusp kind of shape. This is the one. If I would like to really look at center of mass, it might be even outside of that fluid element. So if I talk anything about acceleration for the part where material is not present, it doesn't make sense. To avoid such kind of fallacies, we try to went ahead, define something named tensor, stress tensor at each and every point in the material. Maybe if we are talking about Cartesian framework, this entire sea wave breaking and so on, I can describe by small tiny boxes. And these boxes having rectangular parallelopipe kind of thing. If I'm talking about cylindrical coordinate system, this entire fluid motion might be constructed by those tiny cylinders. If it is spherical kind of systems, maybe atmospheric flows and so on, maybe we require something like spherical kind of systems, and those tiny things we would like to really talk about. So usually forces are always act on the points. Stresses act on the surfaces. That means you pick any tiny element. If I really zoom it up, it might look like that. There are some 6 phases which are bounding a volume. So any material, whether it might be your pen, piece of chalk, fluid, or perhaps computer monitor, or perhaps wind turbine blade, whatever might be, it always consists of these tiny parts. And any tiny part, if I am going to pluck it out, the tiny part always has certain volume which is bounded by surfaces. And the stress actually act on those surfaces. It's supposed to be at the internal point, but that internal point, how small you might be going to divide, you always see small point. So if I am going to really zoom any of that tiny internal point, it might look like that bounding box. And your stresses act on these faces. It's supposed to be defined at a point, but for our sake, what we try to really look at is maybe something, some stress act here, here, here. The component of stresses act on that. Together, if I am going to project this stress component onto particular surface area, I might be going to get force. So in the last class, we have defined something like T double bar. If I am going to project it onto any particular area, maybe this is the one, then I will be in a position to really get T condensing on NDA gives me what is the effective force across that surface. That kind of thing, what we call traction. Leaving apart about these technical names, if I project this stress tensor onto particular unit areas or whatever those directions, effectively I will be in a position to really get these forces. And during our later part of the course, we will see that the stress tensor can consist of 2 components. One is pressure terms, other one is viscous stress terms. How to show that we will see later. And why we are trying to do all this thing is force has to be generalized in terms of stress tensor. Once the stress tensor is defined, it's always be nice to know that what kind of compression it is experiencing, what kind of stretching it is experiencing. I would like to really distinguish these 2 things. Something like if I take an element, I know what is the stress tensor, but whether it is under complete compression or is it some kind of stretch, rotation, this kind of things are happening. To really understand that, we will decompose the stress tensor into two components. We will see that. But as of now, what we can really take it for granted is maybe once we know those stress tensor, we will be in a position to really calculate forces. If I know forces, then I can apply F is equal to ma. And especially to talk about that ma, acceleration, velocity, displacement, whatever the study, we go ahead and do that kind of study, what we call kinematics. We don't care about, though forces are very important, stresses are very important. We know that somehow these are manifested or acting on these elements. That is the reason something like this ocean wave start moving in this direction. What kind of displacement it has, what kind of stretch it has, what kind of rotation it has, how much twist it is experiencing. This kind of quantification, if we can do, we call that kind of study as kinematics. Is that fine? Hello?
Yes, sir.
Wonderful. Fine. So especially in that kind of study, where we try to know about displacement or position vector, maybe velocity, acceleration, the kind of stretch, deformation, we will call something like vorticity and so on, so kind of thing. That study require a special frame of reference. That kind of frames of reference we usually associate it with either Lagrangian frame of reference or Eulerian frame of reference. Why we are trying to distinguish is, people over the time realize that if billions of particles are going here and there, I mean, even though I might be defining something like stress field, even if I am going to project it onto particular kind of directions to get forces, tracking all these billions of particles is not a easy task. And there is no experimental way you can really track them. Think of something like millions of billiards balls are going here and there. If someone asks you, tell me what is the velocity of each of these particles, next instant of time where they will really move. Unless you count all these millions of balls, track that, store their data, you will not be in a position to handle that. Especially in 17th, 18th century, people couldn't really do that. Even in 21st century, we are in a position to track maybe 100 particles or 1000 particles, but not more than that, at least at experimental level. We do not have instruments to really distinguish them, whatever the tools we use. So it requires a special frame, what we call Eulerian frame. Lagrangian frame means you track each and every individual particle, talk about its velocity, acceleration, whatever those things, then it is Lagrangian. I don't care about individual, but collectively I will be going to talk about it. Then we call Eulerian. So let us begin it in this way. We have a one-dimensional system. This is the road. Can you see the road on which 3 cars are moving in the rightward direction towards east? What are the colors of these cars?
Blue, red, and green.
Blue, red, and green. Now think of a 18th century situation where no GPS, nothing is available. Maybe cars are these just steam engine based kind of cars, or cars just developed carts. You can think of them as carts also. Now, how to know velocity and acceleration of a red color car? What I am supposed to do? This is the question we would like to ask ourselves. There might be red color car, green color car, blue color cars are going on. Maybe instead of 3 cars, let us think of 10 cars. Maybe think of 100 cars are going on. and someone is asking you, can you really tell me velocity of a particular car, particular here, maybe red color? What I'm supposed to do? Can one of you answer me? What are the ways you can really measure that velocity? Think of like 18th century. Hello? Hello?
Yes.
So what you have to do? Maybe the easiest way is you connect a rope, a bundle. The car is moving. Rope is also extending. Now to the rope, you might be making a pointer. Maybe that rope entirely having something like a scale, divisions. First division, 100th division, 1000 division, 2000 division, and so on, so kind of stuff. You stand at one location, the rope is continuously going. The car is trying to drag this rope. Based on the division, you have something like a watch. You try to measure that, this is the speed of that red color car. Is that right? That is the easiest way what one can really think of. No, Raja, I can have a bit sophisticated thing. What you can do, maybe to the wheel, you can connect something like a dial gauge, like a wheel, gear. So as wheel is rotating, gear is also rotating. So as gear is continuously rotating, there will be a lever which really draw the position of this on the paper, so that you can really know how far it really went. Or based on how many rotations it does, based on the lever arrangement, there will be indices through which you can really count how many indices it has moved over the time. You can measure that velocity. Because it's one directional thing, it's not taking any turn here and there. That's the only way one can really measure the velocity. Maybe a bit sophisticated like 19th century. If you want to know the car speed, the easiest thing is you have to sit in the car, look at the speedometer, so that you can really note it down. I started my journey at 8 o'clock till 9 o'clock. Every minute or every 10 minutes, I'm going to note it down what is the speed, so that I will be in a position to really plot something like velocity of the car as a function of time. Is this clear? Hello?
Yes, sir, yes.
So every instant of time, how close, how accurate you might be, you are going to really track that particular red color car. If I am going to really get such kind of velocities, we call those are Lagrangian velocities. You have to sit with the car to know that. Or you need some kind of GPS arrangement. You all the time, you are going to track only red color car. The same procedure, you can repeat it even for green color car, blue color car also. If I do that, I might be going to get such kind of plot. The vertical axis is velocity, horizontal axis is time. Blue color car have one particular kind of velocities, red color car has another kind of velocity, green color car have another kind of velocities. So as number of cars increases, you will have many more cars going here and there. Now, if I would like to really calculate acceleration of that particular car, what I have to do is, what I have to do, I already made a time series of velocity with the time. So time series as a function of what is the velocity, I'm going to see. What is time? What is velocity? What is time? What is velocity? And so on, record. Now, if I would like to calculate acceleration of red color car, what I can do is maybe pick any two neighborhood points as close as possible. Now take this ahead. Let us call this one as t plus 1 time, and this one is t. So maybe v at t plus 1 time minus v at time t by t plus 1 time minus t. That gives me acceleration of the car. If we are going to calculate it in that way, we call Lagrangian position, Lagrangian velocity, Lagrangian acceleration, because we are going to tag something like a red color car. Similarly, only for green color car, I can calculate Lagrangian position, Lagrangian velocity, Lagrangian acceleration. Blue color car also I can do. Right? Now let me ask you a question. Can I calculate standing at one location? I can only see some fraction of a car by standing here. What I mean is somewhere on the road, on the other side of the road, Raja is standing there. Okay. His view is focused only to this much level. Wherever dash dot lines are there, he can only view up to that level. He is completely packed up on his head. So he can see only fraction of that road. Unless some cars pass by him, he will not be in a position to really see whether it is red color car or blue color car or green color car or whatever. Fine. Now he has a stopwatch. He start observing on the road by some laser gun or some kind of speedometer, odometer, whatever this kind of thing. He just triggers that gun so that it hits, reflects back by Doppler effect. He is going to find out what is the velocity of the car. Let us assume it in that way. On the road, I mean, on the side of the road, he is standing. Raja can see only part of the road. Cars are zooming, zipping over that road. Sometimes he might see cars, sometimes he may not see any cars. Now he has a stopwatch. He start recording velocities. When he start recording those velocities, because he's a color blind guy, he can just track only car velocity, but not any other thing. Let us assume that kind of situation. Now, next instant of time also, will you see the red car or blue car or green car? What is your comment on that? On road, cars are zipping. It's not just 3 cars, maybe 30 cars, 300 cars, 3000 cars going on the road. What Raja is going to begin is at 8 o'clock morning, he just went onto that road using stopwatch. He's just recording. Why I use color blind is he's not really focusing on the car, but he's continuously pressing that laser gun so that because of Doppler velocity or Doppler effect, he is going to sense something like beep, 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 beep kind of thing. Whenever he sees a beep, then he is going to record the velocity because that beep associated with some number. Next instant of time, there is no beep. After 10 minutes, again, he starts sensing some beep with velocity. Can he really subtract first velocity minus second velocity to say something like acceleration as velocity, what he has measured at some time t plus delta t minus velocity at some other time t by delta t. Can you calculate that quantity and say that acceleration?
No.
Is the problem statement clear? At t plus delta t, he might be seeing some velocity. At t, he might be seeing another velocity. This delta t, how close, how large, it depends on what kind of accuracy he would like to have. That's the only difference. Can he call that one as acceleration?
No,
Hello?
sir.
No, sir.
No. Why?
They are different cars, so we cannot associate
Precisely.
it with one
This
car.
is the problem what fluid mechanics guys face it, or the complex systems guys who handle billions, zillions of particles face precisely this problem. You measure velocity, next instant of time, there is no guarantee the same fluid particle might be there. Maybe some blue color particle might be coming. Next instant of time, green color particle might be coming. Maybe and so kind of stuff. So he cannot just stand at one location, start shooting laser to collect velocities. He can collect velocities, there is no problem. But if he climbs something like acceleration, one has to define acceleration of what? Are you defining acceleration of that particular particle? That question always be a dilemma for him. So he cannot really do that kind of calculation to calculate something like acceleration, because on two different systems you are calculating. Think of something like there is a tennis ball ballistically moving and also a rocket is moving. You measure at one point of time rocket velocity, you measure at another point of time tennis ball. You subtract these two velocities divided by how much time? Acceleration you are calling. But this acceleration of what, whether it is rocket or ball, we cannot really define. And it is meaningless also to define such kind of quantities. However, standing at one location, trying to get velocity, or maybe standing at two different locations, maybe Raja might be standing, and maybe Kunal also at some other location, both are parallelly measuring velocities, is much easier thing to connect further. If that kind of things we are employing, we call Eulerian velocities. You locate or you stand at one location, at a precise location, you know where you are measuring, you track velocities. Then that kind of velocity is what you call Eulerian velocity. Maybe atmospheric flow. Clouds are moving here and there. There is a breeze going. You don't really go with the breeze. You don't particularly track that particular fluid particle. What you do is, maybe you sit at your room. There is a probe which you penetrate into breeze. Maybe because of I square RT, whatever you heat it, hot probes, hot wires. This is the terminology what fluid mechanics guys call. You heat something like a coil. How effectively that cooling is happening? In some sense, you calibrate in terms of velocities. Say that velocity as Eulerian velocity. That is much easier to do. Maybe think of there's a flock of birds. Maybe billions of, or maybe at least millions, maybe at least thousands of birds are going together. Maybe they sometimes in the dawn they might be making some circular motion and so on. Identifying which bird has which velocity is not an easy task. For that, what you have to do is you have to put something like a transmitter to the birds, maybe some 1,000 transmitters to each of these birds. Then only you will be in a position to really talk about all those velocities, all those accelerations of that bird. Otherwise, you cannot distinguish each of the bird. Here, for our visualization purpose, though I have shown something like blue color, red color, green color for understanding, in reality, if you look at breeze, can you really identify each and every particle? We may not be in a position to do. Maybe in river, each and every fluid particle can be really measure or realize that it may not be possible. So measuring at math level is quite easy to define that this is Lagrangian velocity, I can calculate acceleration and so on. But when these kind of millions of particles are going, I cannot really test the hypothesis. I cannot prove anything. I cannot really measure the things. Then it is useless quantity. So the useful quantity is your Eulerian velocity. But if I have Eulerian velocity, I cannot really calculate acceleration. If I don't know acceleration, I don't have forces. I don't have any stress projections. I don't know where exactly they will land up and so on, so kind of calculation I cannot do. So this kind of two frames of reference, if we can carefully connect it, we are done with the problem. That is the strange and strong notation what Euler has tried to connect it. Though this Lagrangian Newtonian kind of mechanics is pretty clear, like you track what is the big deal, but in reality is a very big deal. So Euler really jumped onto that, saying that, hey, you don't have to really track about all these things. I'm very good applied math guy. I know how to really connect that kind of transformation. If I can really give you that, you just ask one of your friend to stand next to you, measure two velocities. From those two velocity information, I can really tell you what is the acceleration of any particle, whatever passing through that probe. That kind of crazy calculation what Euler has done. And that is the place what we are trying to. Now think of a crazy situation from one dimension to three dimension. Let us go ahead. To begin that three dimension, let us begin with two dimensions, 1 to 2 to 3. Now XY plane I'm showing you. There is a XY plane. Vertical axis, what I want to really measure is velocity. In case if I'm going to measure, the velocity is V. Now the red particle, green particle, blue particle, perhaps might be shot at the same location. They might be shot at the same location, maybe at different times. Let us think of it in that way. That means I have a barrel gun, I'm shooting it. It's not necessary that all these bullets, whatever coming out from that barrel gun, may not be having same velocity. It depends on local breeze. It depends on how much perturbation already gun is having, how shaky I'm holding, and so on. So things really change these directions, velocities, and so on. Let us consider 3 different instances of time from the same location. I shot a particle. So the red color over the time goes along this particular path. Can you see the red color path in the XY plane? As it is going, its velocity might be changing. That is the thing what I am going to measure in the vertical direction, or V. Similarly, blue color, it might be having different kind of path on the XY plane and having different velocities. On the green, you might be having different kind of path, different kind of velocities. Maybe think of there is a river. River is originated at one location, let us assume. There are many particles which are coming. It's not necessary that all these particles go together. They might take some swells here and there. There will be branches out and many kind of things happens. That kind of situation what we are having. So now if I would like to really calculate velocity of the particle, what I have to do is first identify whether I'm going to do red one, blue one, or green one. Along that path, over the time, calculate dr by dt, the position vector. Then only I will get velocity. Only on that red path, try to calculate dv by dt. Then I will get acceleration. That's the way we have to do. If we are going to do that, we call that one also Lagrangian frame. Individual particles are tagged, whether red, blue, green, whatever that. Sorry. Now let us think of a situation like what I asked. When Raja is standing at one location, he might be going to sense only one particular velocity. Next instant of time, blue color car might be coming. So he cannot really calculate red color car velocity minus blue color car velocity by delta t as acceleration. So this we cannot call as acceleration of the car. Now, if that is the case, how Raja is going to calculate acceleration of red color car, acceleration of blue color car, or acceleration of any particular fluid particle, whichever it is moving. So let us look at that. Maybe Raja has asked his brother help, Ram. Raja and Ram both are standing next to each other. A very tiny distance, delta x is separated them. Both Raja and Ram walk together with their kind of velocity measurements. Together they press their operators so that they measure the velocities. And what they try to do is they construct something like a table. Time, whatever the measuring instrument Raja is holding, velocity, he will record it at that given instant of time. Maybe first second, maybe second, third second, fourth second, and so on. At the same time, Ram also start recording the velocities. Calculus velocity, calculus velocity, calculus velocity, calculus velocity, calculus velocity. Acceleration of red color car, what I am showing it by red A. What Euler has given us, relation, which we will see later. You pick only velocity of either Raja or Ram. It doesn't matter. Pick one of them. Maybe the easiest choice is pick red one. In that sense, it's not about red, it's not about blue, it's not about green, but velocity what Raja is measuring. Because of that reason, I'm going to show this one as violet color. Is this step clear? Hello?
Yes, sir. It's clear.
So only Raja is measuring some velocity as a function of time. Only we are going to calculate any operation on that. Now, because I have as a function of time at Raja location, I will be in a position to calculate over the time what is del V by del T. Del by del T is basically straightforward differentiation. Though it looks like partial differentiation at this point, let us assume that second information minus first second information by 1 second. Third second information minus second information by 1 second. Fourth second information minus third second information by 1 second is what I mean del V by del T. Only at Raja location, I will be going to calculate. Already at Raja location, I have the velocity at any given instant of time. So that means when I am going to calculate del V by del T, if I would like to have at second, what I am going to do, second minus first second by 1 second gives me at second velocity. If I use backward difference. At the same second, I already have a velocity that is here, second velocity. Now I need something like a correction term del V by del X. Why we require, we will see later. How I will calculate del V by del X? Ram is telling me or giving me something like a velocity. Raja is also giving us a velocity. Calculate difference in Ram velocity minus Raja's velocity by how far they are separated, delta X. So to calculate del V by del X, what we are trying to do is V Ram minus V Raja by delta X gives me del V by del X. That when I have to calculate at second. Now, what Euler has proposed as, if I do this kind of del V by del T of Raja and V of Raja, del V by del X in between Raja and Ram, if you can calculate, add it, that's supposed to give you Lagrangian acceleration of that particular color car what Raja at that given instant of time seeing. Is that clear?
So how will we calculate
Okay, the mathematical definition, we need some time to really describe that. But what Euler has proposed, you do this thing. You don't have to really track billions of particles. Just Raja, Ram is good enough. Whichever particles really passing over them, they can always record Lagrangian velocities. Once the Lagrangian velocities accelerations are known, immediately you can really bring in these forces. You can really understand complete dynamics of that particular particle or any particle, let us say. That kind of beautiful information what Euler has given. And typically at fluid mechanics, we will shortly see how to derive that. But the definitions are clear to you. Is that right? What versus what we are calculating?
Yes, sir. It's clear now.
Okay. Now, this temporal at a given location, if we are going to track velocity, calculate difference, we call that one as temporal acceleration. This term or this term, what we call as spatial acceleration. So on Eulerian frame, you will be having both temporal acceleration and spatial acceleration. When both of the things you measure it, calculate it, add it, then you will be in a position to really get an acceleration of any particular car at that given instant of time. You may not be knowing red color car. It may not be blue color car. But at that given instant of time, you have whatever the fluid particle passing, that acceleration, you know. Now let me put it in this way. On Yamuna Express Highway, there are hundreds of Maruti Altos or thousands of Maruti Altos are going. Maybe thousands of Porsche cars are going. BMWs are going. Everything looks one and the same. You can't distinguish each other. And I don't care about which Porsche. But at that given instant of time, what is the acceleration of that particular Porsche? That kind of acceleration, if I know, I can really know what might be the trajectory of that Porsche. That Porsche car takes this much amount of time to really travel. This is the way it deforms. This is the way it crashes. This is the way it impacts. This is the way it fly off from the ground. That kind of information I can really tell you because I'm going to have acceleration. Any further dynamics I can connect it. Clear?
Yes, sir.
Okay, wonderful. If that is done, now it becomes so easy for us. In most of our fluid mechanics course, we handle only Eulerian fields. From that information, we calculate required Lagrangian accelerations, apply Newton's equation of motions. And these Lagrangian frame reference, instead of showing like your plus 2 d by dt, in fluid mechanics is traditional. Why? We don't know. But this traditional way to show that the plus 2 level we show small d by dt, but in our fluid mechanics, solid mechanics kind of courses, we usually show by capital D by dt. And that term, what we call material acceleration or Lagrangian acceleration. You identify, you tag one particular material, and that acceleration you are going to somehow estimate from the field description. That kind of thing, what we call material acceleration or Lagrangian acceleration or total acceleration of the system. Anything you stand at one location, try to measure. You call that one as Eulerian velocities, Eulerian fields. Once you know that Eulerian field, Eulerian velocities, you do this Euler's magic to get acceleration of that particle. Wonderful. Now we understood the concept. Mathematically, we have to describe that. How to really show that Lagrangian acceleration equal to del V by del T plus V del V by del X, or in 3 dimensions, V dot grad V. How to show that? For that purpose, we need to know step by step this mathematical procedure. Now, let us stick with Lagrangian information. Now, if I am saying on the Yamuna Expressway, I need to know what is that Porsche car's displacement. What I am supposed to do? Where do I measure? Can you tell me? Hello? Guys.
So could you please repeat, sir?
Porsche or series of Porsche cars are going on roads, especially on Yamuna Expressway. It might be having multiple lanes here and there and so on, so kind of thing. Maybe there might be traffic and some guys are really zipping, taking nice spiral kind of thing, wavy kind of paths and so on, so kind of stuff. It is happening. Somehow through GPS, somehow by integrating that Lagrangian velocity, or somehow leaving a trace from Porsche car continuously, I might be sprinkling something like colorful patch. On the road, it really show me something like a nice trajectory. Or maybe I'm going to drop some paper rolls so that I will know every given instant of time what is the track done by this Porsche car. That is the one what I'm showing on x-axis versus y-axis. Can you see that?
Yes.
Hello?
Yes, sir.
Yes, sir.
Trajectory we will call Lagrangian trajectory. It's only for that particular red Porsche, blue Porsche, or green Porsche, or one of the Porsche, or one of the BMW, or one of the Maruti Alto, or one of the Nexon, whatever that car. It can have complicated trajectory. And what we are trying to do is, from Connaught Place, I always measure. Okay. For that, I require something like a position vector. It can be because cars are always go on the roads. Connaught Place is the origin. From there, what is the position vector of that car? I may be on the road, or aerially I might be measuring that position vector. There might be buildings, trees, all these things are coming, but I don't care. But I just would like to really point a position vector. That position vector, what I'm trying to show here, capital X naught. Somehow I have identified morning 8 o'clock at time T naught. The location of Porsche car is at Dwarka. Not Gujarat Dwarka, but Delhi's Dwarka from Connaught Place. That position vector, what I am calling capital X naught. Typically in fluid mechanics, again, this is a notation. Capital X kind of notations, we use it for Lagrangian. Usually, there will always be relaxation and so on. At least for next part of our discussion, capital X naught is X is a vector, position vector, which is present at morning 8 o'clock from Connaught Place to the Dwaraka location where that Porsche car is present. Now from Dwaraka, it really went, and maybe it went from violet line to yellow line to violet line to red line and so on, so kind of thing it went. Maybe at one point of time, it reached Rajiv Chowk. So from that Connaught Place to Rajiv Chowk, we are showing position vector. The description, what we would like to really say is, if you be careful, all the time, I'm going to talk about only that particular Porsche car. That's the reason capital X bar is the present position vector of the Porsche car at Rajiv Chowk from Connaught Place, but which has originated at Dwaraka. So that information I need to really say. Can you see that X bar naught, comma T naught? Hello.
Yes, sir.
This means tagging. Instead of tagging by red color, blue color, green color, at that given instant of time in the river, morning 8 o'clock, maybe what is that fluid particle? It start moving. It's already acquired some velocity. I don't care. It's not necessarily to be begin at zero velocity. It might be coming from somewhere from Panipat, reached this Dwaraka, and then went through this Rajiv Chowk, maybe towards Noida. It is going. We don't care. But point is, at that 8 o'clock, what is that position? That is capital X naught. And that information throughout the time I have to carry. Then I will call this as tagging, and this is Lagrangian trajectory of that particle mathematically, which is always moving. The position vector X bar is continuously moving. If I can really calculate del by del T of capital X bar, I know the position vector, how it is changing. Only for that particle, I will calculate Lagrangian velocities. Is that clear?
Yes, sir.
And is it del by del T or d by dt?
So del by del T, d by dt is just for convenience of our notation we use. You have to temporarily switch off our typical partial derivatives as of now. As long as I'm tagging a Lagrangian trajectory, whether I calculate d by dt on Lagrangian trajectory, once I identify del by del t, they will be one and the same. As long as I'm tagging, I'm going to do only differentiation on that. Clear?
Yes, sir.
What I mean is x bar, which is originated at x naught, t naught, but time t is present location, minus x bar, which is at x bar naught, t naught time, divided by delta t, supposed to give me velocity of that Lagrangian particle. Is this clear?
Yes, sir.
Yes.
That I can do in this way, I can do it in this way. It doesn't matter. But I should be really careful. That is only Lagrangian quantity. But because Eulerian, we distinguish space and time separately. Usually we apply that notation only for Eulerian field. We usually don't represent that on the Lagrangian at fluid mechanics. But when it comes to solid mechanics course, you will apply. But you should know that I'm talking only for Lagrangian for talking about that velocity, especially when I tagged it. As long as that clarity is done, is there, we are done. Fine, guys? Hello?
Yes, sir.
Wonderful. If that is clear, let us move on, because notation is the one which usually becomes bit difficult task to understand. So we understood mathematical notation for Lagrangian also. Just give me 10 more minutes and we'll close this session. Now, if it is Eulerian, what I have to do? If it is two-dimensional, Rajiv Chowk, whatever, this kind of thing, I continuously shoot something like a laser pointer. Maybe I would like to really track not something like only this Porsche car, but even behind Porsche car, there might be BMW. Behind that, there might be Tata car. Backside of that, there is another car. Then usually what people do is they shoot a laser sheet. So you will have a laser pointer. There will be something like knife edge. So diffraction happens. It's really split. That entire laser sheet, because of mirrors and other kind of thing, you will focus something like a plane or laser sheet. You will see something like a partition. It's not real partition, but a partition of rays. That is the one what I'm trying to show by that blue color. So you shoot that laser, you somehow get velocities of all these fluid particles, whichever crossing that laser sheet at that kind of time, get the velocity record. There will be some computer processing happens and so on. You shoot a laser in this room, something like a partition, because there is a fan. Air particles are coming, going, and so on. So kind of things are happening. Maybe dust particles are also coming, going, and so on. So kind of thing. And because there is a mixture of these particles or fluid motions or whatever, that laser, whenever it shines on these particles or whatever, it reflects. Based on that reflection, one will be in a position to really track through cameras to get all that information. It looks like very complicated thing, but measuring is very easy. Once you have this kind of instruments, you just shoot it, you get that, your computer really process, gets your entire velocities at that given instant of time. That is the thing what I'm showing by these little arrows. At each little arrow, there are different kind of fluid particles. Can you see that? Hello? I'm going to shoot a laser sheet so that BMW, Porsche, all these things are piercing through that laser sheet. And I have some camera on top or size or whatever. How this laser sheet is going to reflect and so on, I will be in a position to really measure what is the size of the car or perhaps at least the velocity of the car. That's the way I'm going to really record. Clear?
Yes, sir.
Think of a situation, some person is walking, you are the one who is focusing torchlight. Whenever person go and you have put a camera behind the person towards the wall. Whenever a person moves, there is a shadow and your camera really captures shadow. That means some person has walked. How long that person shadow is present, Based on that, you can really calculate velocities. That kind of velocities, what we call Eulerian velocities. We are not sitting with the person. Based on the shadow, reflections, and so on, we are going to measure. Okay. So at that point of time, when you shoot a laser, there might be Porsche car, there might be BMW, there might be many kind of things. And it gives you complete information of all these velocities. It gives you a field. Instead of particle, we call such kind of things as fields. And that kind of description, Eulerian field description. Whatever the velocities you see, you straight away measure based on, oh, this is the x location, y location, what is the velocity? This is the x location, y location, what is the velocity? Maybe let me use some other color. This is the x location, y location, this is the velocity. X location, y location, this is the velocity. At that given instant of time, at that given positions, you know the velocities. And these velocities are collection of many particles. Your red particle might be present, may not be there. Some other instant of time, your tagged Porsche car might be passing through that field. Okay, great. Now, I would like to really bring this connection, Lagrangian, Eulerian. So already we learned something like notation, whether it is xy plane or x1, x2 coordinates is just indicial notation. Usually we go with indicial notation to represent coordinates. On that, there is a Lagrangian particle which is at a given xi of 0 location, and time what we are going to measure, let us call that one time as t cap time. It is at t0 location, time 8 o'clock. It is at Dwaraka. This is that Dwaraka. Time t0 is 8 o'clock. Over the time, I'm going to measure only for that Lagrangian particles. So what I'm trying to say is, the measurement time is t cap, where t cap is 8 a.m., 9 a.m., 9:30 a.m., 10 a.m., and so on, so kind of stuff. Why we are using cap? Just to distinguish this time record, what I am measuring Lagrangian is different from the time record, what I am going to measure on Eulerian. Just to distinguish that, I am going to use cap. Otherwise, later part, there will be confusion. This time, that time, there is a confusion. So what I am going to do is, at t0, there is a Porsche car started in Dwaraka at morning 8 o'clock. That means I know the position vector x bar 0, t0 I know. Now onwards, the time is t cap is equal to t0, t01, t02, t03, t04, and so on, so stuff. And just to distinguish, I'm going to really put another identification suffix L, represent Lagrangian. This might be for velocity, it can be temperature, it can be density, it can be acceleration, it can be concentration, it can be any fluid property, thermal conductivity, any kind of thing. So to have such kind of relaxation, instead of using velocity, acceleration, we are showing something like a variable T. Maybe temperature of that Porsche car engine is Lagrangian quantity. Maybe the inside temperature of that Porsche car is Lagrangian quantity. Maybe the fragrance of that Porsche car inside, Lagrangian quantity. It can be anything associated with that. Is this notation clear first of all? Guys?
Yes, sir.
Yes, sir.
Now, somehow measured it, I recorded it and stopped it. At the same time, without my notice, maybe Ram also started calculating, my Judva brother also started calculating this Eulerian temperature field, Eulerian Lagrangian, Eulerian whatever this. He is at some location. He is not coming with me. He doesn't know anything about my Lagrangian. Okay, fine. If I represent that, that's we call Ti xi comma t. So the Porsche car might be there at his location. Maybe BMW car might be there. Maybe some other fancy car might be there at that particular xi and at that particular time. It's not necessary that it has to be T0. Maybe my Porsche car started at T0. Raja started tracking all those times T cap. Maybe Ram started measuring whatever the cars goes via Rajiv Chowk from 9 o'clock onwards. That quantity, what we are calling T E X I T. Is this clear? Hello?
Yes, sir.
Wonderful. If these two clear, now I would like to bring the same description of Porsche car, whether it is on Lagrangian or Eulerian. That means, think of a situation. Suman or Mohit or whoever so, they are at Noida. The car passes via Dwaraka, Rajiv Chowk, Noida, maybe towards Ghaziabad, maybe towards Meerut, Dehradun, and so on so stuff. It is going. Mohit and Suman stood at this Noida location. Only they were told by walkie-talkie phone, whatever this kind of thing. Porsche car with so and so kind of number. When it passes, guys, you just measure Eulerian and also Lagrangian thing. Okay, is this clear?
Yes, sir.
The same experiment, everyone is repeating. Maybe first Raja has calculated all that Lagrangian trajectories. Ram at Rajiv Chowk also started measuring. Maybe Mohit and Sushil or Ujjwal, whoever, so they also started measuring at Noida. Let us assume it in that way. These three guys talk about the same kind of thing as long as they are going to really see the same Porsche car at the same time and same location. Otherwise, they cannot really talk about anything. They cannot talk about that particular Porsche car of certain number unless parallelly they observe the things at the same time, at the same location. Is this clear?
So could you explain
Srijan.
the equality again?
Okay. Raja always tracks Lagrangian thing. All the way from Dwaraka, Rajiv Chowk, Noida, Dehradun, Meerut, Dehradun, and so on. Ram measures only at Rajiv Chowk. Maybe Suman and Srijan, whoever so, they measure at Noida. Whether Ras says something, Ram says something, or Srijan, whoever so guys says something, as they will be saying something which is same if they measure these quantities at the same location, same time. If, then only they can really say that we all do the same thing. Is that clear?
Yes, sir.
If they are at different location, they cannot straight away equate them. Is that clear? Hello?
Yes, sir. Yes.
First of all, let us look at this one. Do you understand TL xi0 t cap is a Lagrangian trajectory which already we have it somehow? Or parallelly, everyone is giving information. Someone at computer center tracking all these kind of thing, getting this information. That way also you can really think of. TL is a Porsche car started at Dwaraka at xi 0, t cap 0. But when I don't put t cap 0, means is the trajectory of the Porsche car at any given instant of time. It can be at t0 cap, it can be t1 cap, it can be t2 cap, and so on. Is the complete trajectory Lagrangian thing. That equals to my Eulerian thing at that given instant of time when my position of the Porsche car, I measure at Rajiv Chowk for the same Porsche car at time t cap. Is this clear? The notation? Let us focus only on the Eulerian trajectory. So let us use some black color, some other. Oh. Eulerian information, it can be density, velocity, concentration, whatever at Rajiv Chowk you are going to measure at a given xi location, which precisely on that Lagrangian trajectory. My xi location where I am going to stand is on the Lagrangian trajectory. That is this information. I might be at Rajiv Chowk, but my Porsche car is supposed to pass over Rajiv Chowk. How I am showing that math way notation? Ri is the position vector of xi0 t cap which started at 0 is position vector of that Porsche car which is at that Rajiv Chowk, not any other path. I may not care about what is the Dwaraka. I may not really care about some other location. I may not really care about some other. I may not really care about Mayur Vihar, nothing. I care only about Rajiv Chowk. At that Rajiv Chowk, when I am really measuring, the Porsche car supposed to pass over Rajiv Chowk. That means mathematically, the position vector of the Porsche car supposed to be at that xi location. Is this clear mathematically? Because notation becomes damn important in fluid mechanics. Hello? Hello? Guys, unless you say yes or no, I will not be in a position to understand.
Yes, sir.
Yes, sir. Yes, sir. Yes.
Wonderful. So if that is clear, at that Rajiv Chowk, Porsche car trajectory at that particular instant of time, what I am going to measure is same as Lagrangian information at that path which has originated at Dwaraka but passing via Rajiv Chowk at that given instant of time. This is what we call consistency in these fields. The Lagrangian particle information, Eulerian field, consistent because you are observing the same information. If I simplify further, something like red color ball is going, the path you already know. Now you are going to take a snapshot. The size of the ball of red ball matches one and this, matches only when that particular time if red color ball really pass through that camera. Otherwise, you cannot equate it. That mathematically what we are writing is the position xi supposed to be on that particular trajectory, and on the trajectory at that given t time is equal to t cap of that Lagrangian time. Then only you will be in a position to really describe about that particular red color bar or Porsche car. Clear? Wonderful.
Yes, sir.
If that is clear, now this step is pretty easy to show what Euler has done. Okay, great. Now I'm going to calculate material derivative on the Lagrangian. I can really write it even dTL by dt cap, as long as I know I can write it dTL by dt cap also. So for our sake, just stick with any of these things as long as I specifically denote Lagrangian quantity. Is this clear? The rate of change of concentration only within that Porsche car. The rate of change of AC temperature only within that car. The rate of change of velocity of the Porsche car only for that is this left hand side portion. That means I need to do the rate of change of information even on the Eulerian frame. So because it's a complete derivative, now your partial derivatives really comes into picture. Because when I'm going to shoot on Eulerian, the rate of change of Porsche car, I can't really get it. With the time also, unless I move along with that car, I will not be in a position to really sense that. That mathematically what we are trying to do. The rate of change of this entire quantity with the space and with the time we are going to calculate. Because the material moving in terms of space and time from one location to another location on the Eulerian. So the rate of change supposed to have the rate of change at the given space and also the rate of change in the time. The chain rule comes into picture. So if that chain rule comes into picture, now if I really look at my Eulerian field, chain rule on xi, chain rule on time. These are the two variables. So del Te by del xi. However, xi is the position coordinate of some particular material, the car position coordinate. How that temperature changes at this position and the complete change in that position of that temperature. So dri by dt. Clear? Hello?
Yes, sir.
Fine. Te varies with the time also on the Eulerian field, because next instant of time you may not have Porsche car, it might be BMW car. So del Te by del t, complete derivative. So T of that Porsche car varies. So dt by dt cap. Everything in terms of that Porsche car variation we are going to calculate. Is this step clear? Hello? Any derivative, if I am going to calculate, I'm supposed to calculate on that particular material. I cannot randomly calculate. I can do randomly, only randomly in the sense in a very proper way. The rate of change of that material and that material dependence on time and space I can really do. That is the calculation what we are doing here. So how this Eulerian field information varies in space and how the space of that particular Porsche car going to change with the time of particular time, like your Lagrangian thing. Similarly, how that Porsche car position varies with the time here, the density, temperature, whatever, and the time what you are measuring is your Eulerian, and that actually supposed to be calculated on your Lagrangian stuff on that material. So that del T by del T cap. This represents complete derivative of any material element. If I write it, dr by dt cap, only on Lagrangian we are measuring. That's the reason red color time, which corresponds to Lagrangian velocity of that red color car. Ri, I is index like x coordinate, x1 coordinate, x2 coordinate, x3 coordinate. So Ri corresponds to derivatives ui's, velocities in one direction, second direction, third direction, and so on. That is ui, Lagrangian. Del Te by del T. Now, at Lagrangian, at equal intervals of times, I am going to measure. At Eulerian also, I am equal intervals of time. Same time difference if I am going to measure. Every 1 second, I am going to record Lagrangian trajectories. Every 1 second, I am going to record Eulerian velocities. Then my dt by dt cap becomes 1. Equal intervals of time we are supposed to measure. If I can really do that, del T by del T cap becomes 1. Now this top expression simplifies to del T by del Xi multiplied by Lagrangian velocity of that particle Porsche car at that given instant of time, which we are perceiving as Eulerian. They are one and the same at that given instant of time. So my Lagrangian velocity same as Eulerian velocity at that given instant of time. When at Rajiv Chowk you are going to measure on the trajectory of that, and del T by del T. So what you end up is Euler has done. This is the way one can really connect my Lagrangian frame of reference with Eulerian frame of reference as long as equal intervals of times on both the frames I'm going to measure. Okay. So if I write it once again, del Te by del Xi multiplied by ui completely Eulerian plus del Te by del T completely Eulerian corresponds to my Lagrangian information. My Lagrangian information del TL by del T cap. If I don't use that L, then we usually go with these big letters or small letters, indicating it is Lagrangian. If I am using the suffix L also Lagrangian, then this is also permitted to use. It's more like language. This is the way people say, and we are also following that. There's no hard rule for that. Fine. Now, I'm just rearranging this. Bring this one first, bring this one second. So del Te by del T plus ui del Te by del Xi. If I omit Eulerian, omit in the sense, I always measure my Eulerian fields. I won't measure Lagrangian. I can calculate Lagrangian, but I measure Eulerian. Then I can omit E also. We usually show del T by del T plus ui del T by del Xi on Eulerian field. And this term, temporal derivative of any given property, this is what we call spatial or advection part. In shorthand notation, we show this del T by del Xi. Let us write it expand. If I expand, in the earlier class at initial notation, we have learned ui u1 del T by del X1 plus u2 del T by del X2 plus u3 del T by del X3. The meaning of this entire term is this one, where u1 is x component, u2 is y component, u3 is z component of velocities. T is any property like density, temperature, concentration, velocity, acceleration, any kind of thing. So if I am going to really rewrite this entire story, If it is for temperature, on the left hand side we are showing Lagrangian. On the right hand side we are showing Eulerian field description. dt by dt, Lagrangian variation in temperature, is equal to Eulerian variation of del t by del t plus u grad t. Again, this is a shorthand notation. Now already you are familiar with vector calculus and differential notation. U dot means ui delta j, but condensation supposed to be done on ij indices, which is ui delta it, which is u1 del t by del x1 plus u2 del t by del x2 plus u3 del t by del x3. Because shorthand notation becomes so common in our course. You have to be comfortable. Great. Is this clear, guys? Hello?
Yes, okay.
Yes.
Yes. Tell me, sir. Okay. If it is clear, fine. So this relation holds not only for temperature, it can be even applicable for density. It can be applicable for concentration. It can be applied even for velocities. Even it can be applied on accelerations. The Lagrangian acceleration is your del A by del T plus U dot del of A. The rate of change of accelerations. The rate of change of velocities is acceleration. So any kind of flow properties, you can really write it. Even convective heat flux, d by dt of u multiplied by t. On that also it is applicable. Okay. This is what we call Eulerian Lagrangian formulations or connection between Lagrangian to Eulerian frames. Great. So if that is done, we are done for today's class.